计算题还不到10分，当时好多人说我后计。
Hello, everybody.
Hey, George.
Hello.
Hi, David. Hi, Josh.
So let me screen share and take a look at the notes that we had from last time. And I'm trying to context switch and figure out exactly where we left it. I think it was a combination of tooling as well as maybe optimization metrics. So we're talking about the design method, right? This is the notes. Yeah. So these are the notes that started from that benchmark we were talking about with the various reports, and then the question becomes now that we have some result, how do we arrive at a set of chiplets? And we came up with these notes that you can see here, basically how to start with a design, get some evaluation. So this is where the tools came in, where we can model some of the chiplets, figure out performance cost and everything, and then how to iterate. And yeah, how to use the outputs of those initial evaluations to iterate and come up with a more refined design. And I think we had left it in with questions about the tools, meaning like how do we best extract performance and cost estimates. I think that was the most immediate question, and I can't remember if we were talking about, because we have talked in the past about the interconnect. We're talking in the past about how do we design specialized chiplets for the various applications. But I think we're left it at the tools. Does anybody remember exactly?
I don't remember exactly, but I had a question about the first part about optimizing chiplets for these models. Right. If you scroll down a little bit. Okay, the reasonable design. I guess my question is about the final goal. Are we trying to come up with a kind of iterate over designs until we reach the same performance, or as the benchmark that was done on RTX 90? Are we trying to hit that, or something else?
Yeah, so that's a good question, and there's no one answer, honestly. But in my mind, and let's talk about this. But in my mind, it's maximizing performance given the constraints given to us by the technology, like how much power we can dissipate, how many chiplets and what area, how big they can be, and so on. So we're going to get some constraints from the technology, and then let's try to maximize the performance that fits in that. Now, of course, we can also transform the metric as to something like performance per unit power, because that is more directly related to efficiency, and therefore we can translate it to like future technology, future interposers.
Yeah.
What do people think?
Actually, I guess my question was what you answered, the part about the maximizing the performance, right? Start with assumptions and then see how far we can get that technology. I think that's an interesting exercise. It's my opinion.
Excuse me, Luisa is still running these meetings or what? What happened?
She is going to be here maybe probably the next meeting. It was a unfortunate set of trouble.
Ah, okay. By the way, AstraSim, we looked at it in the AI hardware software co-design as a simulation tool. So how you plan to use it in this project?
Well, so if we're going to use this iterative design process, at every iteration, we have to have an estimate of how well our candidate design will perform. What's the throughput that we're going to get, and what's the power, and so on. And that's especially the performance part is what we're hoping to use AstraSim for. But I don't know if we were adamant about it because I don't
Okay.
particularly know AstraSim. Have you worked with it?
Yeah, we worked with it with a professor in one of the universities. Yes, we worked with him on AstraSim.
So do you think
But
it's a good tool?
we use it for our AI hardware and software co-design, not at the chiplet level.
Okay, is it capable of modeling chiplets?
I can't comment on this. What we can do, we can bring that professor to talk about it or present it in this meeting, and you can make your own judgment.
Actually, that would be wonderful if you don't
Yeah,
mind making the connection.
yes, I can send you his email. One
Yeah,
second, please.
thank you. Yeah,
He usually attend the OCP Global Summit. We can also meet with him personally, but I will send you the information.
thank you. Yeah, that will be very helpful. Okay, so where are we going with this? So there's the tooling question. I guess we'll go more into AstraSim. I think AstraSim in this discussion came up as what we think is probably the most capable tool for this, but we don't know enough about it to be sure that it does everything we want it to do. But I'm not sure if folks have experience with anything else that can be used for this process. Okay, probably not. All right. So
Sorry, I thought I was on mute and I was looking for the unmute button. I can help you out to run some simulations. If there is an example design that kind of, if we have the, how do I say, the block diagram of, for example, design with its constraints, I can run a quick simulation. That said, by the way, I had a slightly tangential thought. You mentioned about power metric, and I remember that one of the things that we started working on last year, if you remember, in the first white paper, it's about power for the different cores, right? The different technologies. So I have the ASAP 7 Gemini core matmul power.
sorry, I messed up my window. Yeah, so the professor is to share. Yeah, I actually know him. Thank you. Sorry, David, you have the power for what? For one of the compute cores?
Yeah, the Gemini core. I have the power for 8x8 and 16x16 doing I think it was FP16, but maybe BF16 matmos.
Huh? Okay, yeah.
I can share that next time as well.
Yeah, so yeah, let's talk about that. I'm sorry if you mentioned it and I missed it. What technology is this for?
ASAP 7.
Step 7, okay. I think okay, so that will be very useful. I don't know if AstraSim has models for memory. Does anybody know?
So as far as I know, and I think it will be awesome if we get Professor Krishna to talk about AstraSim, but really the underlying technology of all of this is Chakra. And Chakra captures everything that happens outside of the compute nodes. All the gather all, reduce all, broadcast, right? All these events that go across nodes and move data around, it will capture that, both in time and duration.
Okay, yeah, so that's very useful.
Yeah, but this is when we are talking about multi-node operation. And I think one question would be, does that target training or inference? Right. I don't know what the different. Actually, a lot of companies have published Chakra traces of their runs, and I tend to think they're training runs, but I'm not sure.
Okay, how do I spell Chakra?
Chakra. CHA. Yeah, exactly like that.
Yeah.
With capital C. Yeah, there you go.
Okay, we're not sure. That's okay. Yeah, but that's interesting. I think so. If AstraSim has some sort of memory model, there's a good chance it has, and you have the compute models, and we have these traces. That's good. Maybe the only thing that we're missing here is if we want to model specialized compute chiplets, or specialized RTL, we might have to find a way to embed that into the model, into the flow.
Yeah, let me clarify. So Chakra, when it says a compute node, think of it as far as I know, one box, which includes all the GPUs and memories and things like that. That I'm sure. But whether it goes deeper into that, I don't think so. Meaning to observe what data goes between the GPU and the memory, I don't think so. That data is generally not published by NVIDIA. You cannot see it.
Okay, yeah. So it's at the NIC level, which makes sense. It's often where the spaces are.
Yes.
Yeah.
So you can kind of plan the overall your data center level topology for training runs, right? If you see what the training run does, you kind of can plan it better. I think that's the overall idea.
Yeah, that makes sense because that's the common use case that's a common design boundary in industry today, is what I meant, the NIC. So like you have the scale up, scale out networks, and you have inside the NIC. But for us, it's kind of, we'll see if we can make use of it. If we build a hierarchy among our chiplets, maybe we can somehow translate that. But anyway, okay.
But David, I think AstraSim uses the Chakra format.
Yeah. It uses an input format, so you can see what the training. Okay, let's assume we are talking about training, not about inference. So it captures Chakra traces about what the training runs do, what data they send around, right? When are they all reading data, sending data to all, and things like that, right? So basically, the leaf in that topology that's sending data is the compute node. And the compute node, as far as I understand it to be, is one kind of like a box, right? If it's box with multiple GPUs, it will be the GPU as a whole, not just the GPU chip, but the GPU with its memory and things like that. If it's If multiple GPUs are represented as one compute node, it will still represent it as one compute node. So you will not see what's happening between GPUs. So AstraSim takes that and will simulate different network topology, how this modeling performs, right? How this training performs. That's my understanding, right? So take it with a grain of salt. I think it will be awesome for Tushar to come over and talk a little bit.
You know, there was a tutorial that he gave with a bunch of people, one of the conferences, and he explained many of this stuff. Yes, bringing him would be a good idea.
Yeah.
I can send a link to that tutorial if you guys want to look at it.
Okay, yeah, I think that would be awesome.
Yeah.
But going back to what we're trying to do, George, one thought was, let's start with a example chiplet architecture, right? That has the compute and the fabric and the interfaces and the memories. We can start with one. I can give you simulation results and tell you how this will, what the performance of this will be. And then we can decide the next step. What do we do? Do we add more compute, more bandwidth, different memory, kind of stuff? Would that work?
Yeah, I mean, yes, but to do that, we need to identify the bottlenecks, right? We need to identify what is the saturated resource, or what is dictating performance. Do we have statistics to do that?
No, we don't, and that's the chicken and egg problem, right? Until we have the bottlenecks will be somewhat hardware dependent, right? Depending on how we design the chiplets, the bottleneck may move between things, right? So,
yeah, I'm talking for a given design. I mean, we're going to start with something, and for
yes.
that given design, can we identify what is the bottleneck?
Yes.
Okay, good. Yeah, that's the important part. As long as we can identify the bottleneck, we can then fix it and then keep iterating like that.
Yes, that's kind of what I was thinking.
How do you abstract the workload that's actually done on the chiplets? Because at least to my understanding, that is a very critical part. You know, you have some set of chiplets because you've optimized them to do a particular task. You have a compiler that goes with that. That compiler then has to do the complex task of partitioning that workload amongst the chiplets, and that would determine where your bottlenecks are. You could take a very simplistic approach and say, well, okay, I have a workload. I know that I have a compute phase. I know that compute phase has a certain tops. So therefore it will finish in X number of cycles on this chiplet. But you know, I don't know if that's is that the level at which we want to abstract this, or is there a deeper level?
That's a very good question, Arvind. When it comes to compiler, there's two approaches we probably should decide and take. One is whether we want to stick with PyTorch as the engine that runs the workload, or whether we stick with a vLLM to run the workload. Right. Once we know that which route we take and what is our hardware architecture, we can tune the compiler to give us the best performance, right? How it actually runs that workload on that hardware, and tell us, okay, no matter what you do, this is the best you can do it, right? You cannot do any better. So we can tune that. I think that is at least off the top of my hand, that off the top of my head would feel like the most reasonable approach, because I don't see a use in running a workload that it has not been optimized for the hardware.
Exactly, and this is the problem that we have tried this, and that is exactly where we have gotten stuck.
Okay. Yeah, let's try again. Let's start with, we have the workload.
Yeah.
The only thing we're missing is the initial architecture, right? We just have to put a stick in the ground and say, this is what we'll start with. and let's see what we get and how much we can tune it.
Can I think I have the other concern, and maybe I'm wrong, but can PyTorch actually understand that, okay, I have a 4 accelerator system and each accelerator consists of 4 chiplets. Can you partition this workload amongst these 16 units?
I
I'm not
think,
sure. Yeah.
Yeah, I'm also not entirely sure. Somehow I think it might be able to do that. But we'll find out.
Yeah, I'm actually a little skeptical, but I think that might be a question we would have to answer.
Yeah, the reason I'm leaning towards it being possible is part of the partitioning is partitioning the memory where the model is loaded in memory.
Yep.
Right. So, and then the computes just take whatever is in that memory and will compute it, right? They don't care what it is, right? They'll just take the memory and compute it.
Correct.
So, based on that, I think there may be hooks in PyTorch to specify which parts of the model in which part of the memory you want them, right? Because we can see the entire memory, that is this many gigabytes or whatever it is, and say, okay, I want this piece here, this piece there, and then run the compute, right? And then gather all the results, reduce, and keep going, right? That's
Yeah.
the reason I'm kind of leaning towards it being possible. But unless we try it, I guess we wouldn't know for certain.
Mhm.
But yeah, if we're able to generate a set of initial results for a given configuration of the hardware, that will be a big breakthrough, and then we can start iterating.
Yeah, I think yeah, we have to put the stick in the ground and say, hey, this is what we are starting with. Let's see what we can get out of it. Who wants to volunteer to do that?
That's the problem, because I can tell you I have never used AstraSim. And
No, forget AstraSim. In terms of hardware, chiplet architecture hardware, right? What kind of compute engine it has, how much SRAM, what kind of interfaces, what memory, things like that. What CPU do we want to model for orchestration of the whole thing? That may be useful.
yeah, that's a good question. I'm going back and forth whether somebody should volunteer or make that a topic for our next meeting. Because, so going back, okay, so let's take a step back. The first question is which workload, and we have enough. Well, we have some profiling results for these genome models that it makes sense to make it the first pass, as long as we have code for it or whatever AstraSim expects as an input. So we can use that. We have the 3 sizes, and we can use that to derive a initial configuration, because for each of these parameters, we know, for example, the compute throughput that came out of the profiling tools and the memory bandwidth. So we have some targets to design for. Does that sound reasonable? I mean, we have a target memory bandwidth, for example. We have a target, compute throughput that we want to achieve. So that will be my.
Yeah, I think that's a reasonable first step. And then we can convert that into a hardware that meets those targets. But one caution: we don't have AstraSim traces for genome motion, and we will not have, because they run on a single GPU. So there's nothing outside of the compute node, no outside communication.
Yeah, so that was okay. So AstraSim takes in traces, and if we have the code for the benchmark, is there any way to put that into AstraSim, or do we have to trace it first?
Again, so we have to to separate along the lines of training versus inference.
Right.
Right. If Chakra does training and here we want to match inference speed, we're talking about two different things.
Right. But so before we even go into that, if I guess what I'm saying, like if we have the benchmark, we have the source code for the benchmark. Is that something that AstraSim can run, or it can only run traces? So we have to generate the traces first.
It runs traces.
Okay. Okay. In that case, maybe we just find what Chakra traces there are available out there and just focus on them and just profile them in AstraSim already somehow and get like basically the same numbers that we have for the genome benchmark, memory bandwidth and compute throughput and so on. Because I'm thinking generating those traces will not be trivial.
No, it's not. So on your last comment, I think PyTorch can dump out the Chakra traces. You can configure it to dump out Chakra traces, so that's not a problem. The genome motion are too small for inference to dump Chakra traces. They fit in one GPU, right? So it all works. Now, when talking about the bandwidth from Chakra traces, the memory bandwidth, I don't know how to convert that into a chiplet level memory bandwidth, right? Because if we're talking about exchanging data, if Chakra are training traces, and the memory that's being transported, that is basically internal, how do I say, intermediate matrix operation results. I don't know how to translate that into actual matrix operation memory bandwidth requirements at the hardware, at the GPU level, right? Do you know how to do that? Does anybody know?
Yeah, not off the top of my head. So maybe we just need that AstraSim primer. But to your point, yes, that benchmark genome is for one GPU. I'm not sure that's a problem, at least to begin with. I mean, is it unreasonable to just replace the one GPU with one set of chiplets and show how it's better?
Oh yeah, we can do that. I'm not saying we cannot do that, but the part that we cannot do is the Chakra traces, because the Chakra traces are outside of the GPU. Right. So if we are talking about,
I see. Yeah.
right,
Okay.
right.
Okay.
That's the separation I'm thinking about.
Okay, I see. Yes. Yeah, you mentioned that. Yes. Now I remember. Okay. Okay. Maybe we just go for a primer and AstraSim, and there might be a set of benchmarks already out there that we can start with. Because if we go back, the same discussion, if we go to use Chakra traces, if they don't show what happens inside the NIC, that might not be too useful for us right now.
Yeah.
Okay, so because we're at the bottom of the hour, so let me see. So next steps, AstraSim primer talk, or I'll reach out. So that's one. The other is try to find benchmark which could be the genome, I guess, but anyway, compatible AstraSim to generate initial results for a set of for a given chiplet configuration. Is that a fair summary, more or less?
I'm confused about the middle sentence. Here's what confuses me. The iteration part that we talked about, your last sentence is iterating the hardware architecture to maximize performance, right? That is inside the NIC. When you say genome, when find a benchmark that is AstraSim compatible, I'm trying to connect the AstraSim, which is outside of the NIC, with the hardware iteration that's inside the NIC.
Yeah, that's true. Okay, so okay,
right.
So the whole point is find a benchmark and some results like compute memory bandwidth and so on. So we can derive a chiplet configuration for that. I think okay. So
Okay, got you. Okay.
yeah, that I mean we just need an initial design. I'm just trying to figure out how to get there. That's all.
Yeah, I thought that the benchmark that for chiplet configuration that comes out of the benchmark that was run on RTX 5090, right, for genome motion.
Yeah, that's most likely going to be it because we have a good understanding.
Yeah.
Okay, folks. Sorry, I have to run back-to-back meetings, but this was productive. I'll reach out to Tushar. Hopefully, we'll get something out. See you in 2 weeks. Thank you, folks.
Hey, George.
Yeah.
Put me down for the power stuff for the compute core sometime in the future. Whenever we have time, I can go ahead and do it.
Okay. Let's see if Tushar says yes, and how much time he's going to ask for next meeting.
Okay.
Probably next meeting, though. Yeah.
Okay. All right. I'll be ready.
Thank you.
By the way, did you look at ML Commons, Chakra traces?
Yes.
Oh, good. What did you find, David?
Those are training runs run by different companies, as far as I know. That's my high-level summary.
Yeah, but I think it can be used by AstraSim, right?
Yes. All right, we'll talk next time then.
Yes.
Since George
Absolutely.
dropped. All right, yeah, bye.
Thank you.
Bye.